Hi everyone, just here to give a lecture on my PhD project, which is Forest 4.0 Integration to New Zealand Forest Harvesting Operations. My two supervisors are Dr. Campbell Harvey and Professor Reen Visser. So there's a lot of data coming, or a lot of underutilized data that's within forestry machinery. And this comes in the form of controller area network, or CAN bus data. Now, what is controller area network? Well, essentially, it's a communication system used in cars, trucks, and machines that enable electronic controller units, or ECUs, to communicate with each other. For example, fuel delivery pressure systems, your accelerator, or your indicators. It was developed by Bosch in 1986, so the technology has actually been around for quite a long time. And in simpler terms, CAN bus can be compared to the human nervous system. So an example I like to give is when you put your foot down on your accelerator, it sends a signal to other ECUs, for example, your fuel delivery pressure to tell it to go up, your RPMs to tell it to go up, so that you can achieve the acceleration in your car. So ECUs essentially control the functions in your car, truck, or machine, such as temperatures, steering, brakes, indicators, and so on. So why do we use CAN bus data in our cars, trucks, and machines? Well, firstly, it's relatively simple and low cost. It's reduced to traditional point-to-point wiring, so saving us about 20 kgs in weight, especially important for our cars. It's easy to access. So now that we've got sort of a system that is like a nervous system that goes all throughout the car, it has a centralized diagnostic port, as you can see on the right here. The green plug is plugged into that port. And this allows us to see all the error codes and what's going on from a centralized location instead of having to go and manually picking out an individual wire. And there's standardization across cars, for example, and machines and trucks. So we're under the ISO 11898 standard for CAN. So it's extremely robust as well. So it's not really affected by environmental noise, and it has extensive error detection. So we're not getting random spikes in RPM of say 8,000, which may have detrimental effects on our engines. It's also very efficient, so it's fast, thousands of CAN frames per second, which you're about to see. So here's a CSV file of a typical raw CAN bus data that we collect from harvesting machinery. A frame is essentially the entire row 2, or the row 2 to 27. Each row is a different frame. And so the real key things that we look for in a CAN frame is the ID. And this tells us pretty much what it is. It's sort of its name or its identification, and then the data bytes. So essentially, this is all the data that comes along with it. So it could contain engine speed, fuel delivery pressure, the switches to your lights. And so, as you can see from the previous slide, it's pretty much impossible to tell what exactly is going on. It's not in a human readable form. So we need to decode this raw CAN bus data, the raw CAN frames, to physical values that we're able to read and interpret. And essentially, we do this through using a DBC file or a CAN database file. And so there are several sort of standardized DBC files that we find out there. For cars, we have OBD2. For marine, we have NMEA 2000. And for heavy machinery, as well as trucks, we also have J1939. So most forest machinery should be using the J1939 protocol. And this is essentially the language or the format that the CAN frames and CAN data come in. So here I've just taken one CAN frame from that data sheet, and we're looking at CAN ID 0CF00400, and then the data bytes that go along with it. So within our first step really is to identify the parameter group number, and that is found using the CAN ID. So in this case, our 0CF00400 equals PGN 61444. And this relates to Electronic Engine Control Unit 1, or ECC1. And then within ECC1, there are 8 SPNs, or suspect parameter numbers. And these are essentially the data, or the variables that contain the data. So the SPNs are within the data byte. the data bytes. So for our EEC1, we have 8 SPNs. Sorry, yeah, 8. So we have engine torque mode, actual engine percent torque, as well as engine speed and engine starter mode, among others. And as you can see there on the bottom, this is the data bytes, how a data byte works. And essentially, the SPN 1 starts at bit 4 and has a bit length of 8. So engine torque mode data is found within there. So yeah, as I said, we identify which SPN we want to decode. In this case, we're going to look at engine speed. And then we go back to the DBC file and figure out how exactly this can be decoded. So for SPN 190, or our engine speed, we know our bit starts at 24. The length of our data is 2 bytes. It has a scale of 0.125, an offset of 0. Its unit is RPM. It has a min and max value, and there again we see our PNG. It also has a comment, so actual engine speed, which is calculated over a minimum crankshaft angle of 720 degrees divided by the number of cylinders. So I know this slide looks confusing, but we'll step through it slowly. So again, you see our data bytes at the top: F6, FF, BE, 702A, FF. We know through our little chart at the top left that we're looking at starting at bit 24. And if you go to the right there on sort of where it's in binary, you can see that bit 24 with a bit length of 2 bytes, we're after line 3 and line 4, which is 70 and 2A. So CAN data uses Intel byte order. So this, all that means is basically when we have that 702A, we just reverse it and it becomes 2A70. And so we know to get our engine speed, we go value equals 0.125 times 2A70 plus 0. So this 2A70 is in hexadecimal form. We have to convert that into decimal form before we can get our RPM. So how we do that is we use the 2 times 16 to the power of 3. A becomes 10. We times that by 16 to the power of 2, plus 7 times 16 to the power of 1, plus 0 times 16 to the power of 0. And ultimately, this gets us 10,864. So to get engine speed, again, we go 0.125 times 10,864 plus 0, which gives us an engine speed of 1,358 RPM. Cool. So in practice, we don't do it manually like that. We automatically do it using Python scripts and a DBC file or a dictionary file of the J1939 codes. And essentially, we can convert thousands of these codes in a very, very short amount of time and produce the physical values in CSV files to intervals of either milliseconds or seconds. So what sort of data are we getting out of these CAN systems from harvesting machinery or from forest harvesting machinery? So we get some joystick movements and we also get button presses, but this changes depending on the machine. For example, the John Deere 959 felling machine gave us button presses, but the 1910E Forder didn't give any button presses, but it gave all the joystick movements. In general, we usually get engine speed, temperatures, pressures, torques are all pretty similar across machines, as well as hydraulic pressures and temperatures. Fuel consumption, fuel level, and fuel delivery pressure are again standard ones we see coming up across a range of machines. We also have a GPS unit that's tagged on to the data logger, which essentially grabs us the location, speeds, acceleration, and then some machines also have those pitch and roll angles, like the 959, which are also included. We also have original equipment manufacturer signals or OEM signals, and these are signals that are specific to either John Deere, Tiger Cat, or the manufacturer of that machine. And these are signals that can't be decoded using the publicly available DBC files, for example, the J1939. There are opportunities to decode them. However, they do require a lot of time and the right equipment, as well as some domain expertise about what signals we're actually looking for. So in general, we tend to leave these signals alone, just because it's quite difficult to actually get anything good out of them. So moving into sort of that analysis space, on my right here, you can see a simplified decision tree, trying to predict what a forwarder is doing at any given time based on engine speed, joystick patterns, and the speed of the machine. So why we want to actually understand what the machine is doing at any given time is because it's difficult to sort of relate your analysis to anything. Say, for example, fuel consumed when you don't know what the machine is actually doing. So when we know what the machine is doing, we can say, okay, the fuel consumption was this when the operator was loading, and it was this when he was unloading, and there's actually some comparableness there. And machine learning gives us an opportunity to do this, and very accurately using the CAN data that we're getting from these machines. So for an example, the states of a forwarder would be idle, driving, unloaded, loading, driving, loaded, and unloading. And so we take a chunk of data, a chunk of CAN data, and we label it essentially one of those five things. So for example, if we see an engine speed of say 900, we'd move that into, or we'd label that data or that timestamp with an idle label. And this is how we teach the model to learn. So this is called supervised learning. And essentially, we take 80% of our data, we train it on that and check it against 20%, which we keep for validation. So the model learns essentially which variables are most important for an accurate prediction. On the right here, you can see that distance trip and engine intake manifold one temperature were the two key important variables for distinguishing the different states. It also tells us which variables hinder the predictions. So we can see that steering joystick active and nominal friction percent torque didn't really do much for the model and are basically just taking up space and computational time. So we can remove those. And overall, the model just sort of learns the patterns of each variable that relate to the state. So for example, as I said, an engine speed of 900 for a John Deere 1910E is a standard idle RPM. And then the model basically then predicts the operational status based off all this data. So really here, training and validation data is key. So here's an example on the left of a good prediction. So we have very small amounts of misclassifications, and this is essentially where the model's made a prediction on the training data that's not quite correct, or the model's made a prediction on the validation data that's not quite correct, and misclassified it. And these can be sort of fixed post-processing using smoothing functions. But on the right, you can see a pretty poor prediction here. And this is essentially so bad that it can't be fixed post-processing. And you can see, especially with predicted 4 and predicted 3, there is a lot of misclassification going on there. So again, yeah, to create or improve our predictions, so from going from bad to good predictions, there's basically 5 things that we want to do. We want to have good training data and lots of it. So for example, we want, for a forwarder, we want data of when it's just working on flat ground, when it's driving up the hill loaded, when it's driving down the hill loaded. And this gives us sort of a range of sort of scenarios or what the data would be for all different types of forwarder operations. So we can apply the model to a forwarder working in flat forest, as well as hill country, and then on very steep country as well. We also use feature engineering and selection. And this basically means we take, for example, a joystick button or a joystick movement, and we just either turn that into, say, a binary yes or no. For example, you can see in the middle there, there's joystick active. And this essentially has taken all those joystick variables and just turn that into a binary yes or no, just saying, is the joystick active or is the joystick not active? And this essentially simplifies it and can help improve our predictions and save on computational power. Tuning the model hyperparameters. So for an example, for a decision tree, how many nodes or how many trees can be created, especially in a random forest. Treating missing or outlier values. So this is important, especially when we get errors. I talked about error detection in why we use CAN bus, but there can also be some sort of there can be errors that creep through. One I notice the most is especially when the machine goes from an idle state to back up to normal RPM ranges for working. Sometimes there's a huge spike in RPM, and it's just for 1 second or one value, and that just needs to be removed because it will end up confusing the model later on. And then finally, what I talked about, sort of improving those minor misclassifications in post-processing, we can use a smoothing function to do so, so we really get an accurate, 100% accurate model. And then basically we predict. So you can see on the left here, this is just the prediction represented with engine speed. And you can see we go from driving unloaded to loading, back to driving loaded, and then eventually unloading. And we do that, and there's some various idle states in between those. We can also plot this as a pie chart, and we can see basically that nearly 50% of the time we're spent loading, 16% driving unloaded, and only 10.8% driving loaded. But we can see overall we have a utilization of about 95%. And yeah, as I said, once we know what the machine is doing at any given point, we can then it opens the door for more analyses. So for example, fuel consumption. If we look at the bottom left, we can see that our loading and unloading fuel consumptions are very similar, but our driving loaded and unloading fuel consumptions differ quite a lot. And then when we can look at this over a cycle, so this is taken from one cycle. So essentially on the left here, this is the amount of time spent at each behavior or each component of the cycle. So 45% of the time was spent loading in this cycle. But here on the right, we can see the proportion of total fuel used. So 45% loading was spent in time, but it only accounts for 29.5% of the fuel use. Whereas driving unloaded accounted for 21.2% of the time, but equated to 33% of the total fuel used. And on the right there, we can see to complete this cycle, it used 6.12% or 6.12 liters of fuel. Now we can look at different log rates. So on the left here, we can see our proportion of total fuel used for a K grade. And you can see here driving unloaded was that 33%, loading was at that 29.5. But if we move over to the poles, we can see here that 60.8% of the fuel consumed came from the loading. And this is because loading poles there's not that many out there in the cutover, so it takes a lot more time to complete this cycle, and therefore the time spent loading is actually a lot longer and makes the fuel consumption higher. So we can see for total in the K grade, we used 6.12 liters, but for the poles, we used approximately 4 liters more at 10.65. We can also look at our, another analysis is looking at our operator movements. So identify different loading grabs and their effects on productivity and potentially operator fatigue. So using video and CAN bus data, we identified several different types of grabs. So we have our normal grab, our pencil grab, and our slash drop grabs. So here's an example of a normal grab. And essentially there is no hindrance in this grab. He's just gone down, picked it up, not had to do anything, and drop it right down in the bunk. As you can see on the right there, the pattern is very smooth. A pencil grab is basically when the logs aren't buttered up quite nicely, and he has to do this to ensure when he comes to unload it that the pile on the skid is nice. And you can see on the right there is a different movement path from the grab we saw before. And then finally, we have a slash drop grab. And this is essentially when there is a lot of slash surrounding the log pile or the log. And essentially, he's had to pick the log up and drop it down again to remove some of that slash so it doesn't end up in the bunk. You can also see a lot of opening and closing of the grapple during that as well to get that last little bit of slash out. So I know this looks confusing, but this is the operator movements for those three grabs. I want you to pay close attention to the fourth chart here, and this is the chart on the grapple open and close. So we can see in the middle here, this is basically where he's got the pile up in the air, and he's opening and closing the grapple a lot more in the pencil and slash drop grabs than the normal grab. So the operator is making a lot more inputs or conscious decisions here. And so if we turn this into actual number of inputs or changes in the joystick movements, we can see that for a normal grab, we're only using about 2,421 different joystick inputs. For the pencil, we're looking at 2,673. For the slash drop, 2,744. So we can see, yeah, basically there's a difference of 323 movements between the normal grab and the slash drop, and a difference of 252 between a normal grab and a pencil grab. So essentially, when the conditions of the piles aren't perfect, the operator is actually having to make a lot more movements and to make a lot more actual inputs to actually pick these up, which essentially could result in extra fatigue during the end of the day. So we can take sort of this joystick data as well as include other data and make sort of a digital twin model, or take what we've just done a little bit further and actually see or replicate what the machine was doing out in the field on a cloud server using what we call a digital twin. Unfortunately, the data we took from this harvesting machine didn't consist of any of the head data, so we don't know anything about the felling head you can see there, or the processing head. But we hope, working with Waratah and other companies, that we'll be able to figure this out soon. So there is potential to use this sort of technology to help train sort of early career operators and help them to get that extra boost in productivity earlier on than your typical learning curve, with overlays potentially in simulators of an actual good operator working in a real environment. So basically, we can compile all of this work together in a centralized location. So I introduced a system that captures, automatically processes, automatically analyzes, and displays all of this CAN data I talked about before into an online dashboard. And this dashboard can be accessed by the operator, by the contractor, by the owner of the forest, or the owner of the crew, to see what's going on with each one of his or her machines. So for example, it can monitor operations. So how many trees has the felling machine cut? How many have been processed? What is actually on the skid, say at 2:50 in the afternoon? How many have been loaded on that day? What types of logs have been loaded on? And then the second sort of key thing here is it can help improve performance through review. So especially for those early on operators, how many movements they're making for each grab or each cycle, where some improvements can be made, etc. So looking into the future, there's definitely some opportunities to include some of the CAN bus or CAN bus analyses and that dashboard into real life operations, especially for improving the wood flow to skid management and actually understanding what we've got on the skid at any given time. But where we see a real benefit is this sort of system needs to be integrated into the entire harvesting operation. It doesn't work so well when it is just, say, the harvesting machine that has it, or just the forder. All parts of the harvesting supply chain or the harvesting operation need it. There's opportunities to help with human factors and operator training. So yeah, as I said, sort of lowering that learning curve for new operators and helping them to boost productivity early on in their careers. And then there's opportunities to link in with other projects. A key one could be FGR's log ID. So as soon as a log is processed, an ID is created, stamped on the log, and that ID is uploaded to the system I created and sent to wherever it needs to be, for example, to the mill, and say, maybe, okay, we don't want that log, but this log over here has an appropriate diameter and length. We'll take that one, and could create a marketplace like that. But that's, yeah, looking quite a way into the future. So yeah, thank you for listening. If you have any questions about CAN bus or some of the analyses I'm conducting, my email is there. I'll see you later.